Thank you very much. So, yes, what I would like to talk about the next 15-20 minutes is trains and delays and how we can make our life a little bit better, particularly on the Great Western Railway, where we're deploying some new technology in traffic management system. So first, I would like to give you a very brief introduction to signalling and kind of set up the foundation for what we are dealing with, and then move on to our mission critical signaling control system, IC scalable, and then finally illuminate our new revolutionary traffic management platform. So signaling, we've got a lot of tracks on the railway. That's on the infrastructure in which the trains move, but the important bit there is that for most of the UK railway network, that comes with some clever technology that is able to detect which section of the track a particular train is. So that gives us effectively the location of those trains moving around the network. Then we've got signals, which are traffic lights for trains pretty much. Red and green, it's the same as you used to, but there are some differences around amber or yellow, which is kind of telling the train driver how many signals ahead they can travel before they have to stop. And then finally we've got points or switches, which allow us to change direction of travel, move from one line to another, navigate to a junction, and so on. So these are the actual things that move within the infrastructure to allow the train travel where they need to. But what's really important about all that infrastructure is the interlocking, which in our terms is more of a safety critical IoT gateway, which aggregates a number of those devices. So typically an interlocking will be tens of tracks, signals and points. And what it will do is make sure that when you make requests for certain things to happen on the railway, it will ensure that it's done in a safe manner. So as an example, you've got two lines merging into one. The interlocking will make sure only one train can get a green signal and move safely onto that piece of track. And that's where and then kind of briefly about the interlocking. So we started with fully mechanical ones in the 1840s, into electrical ones, and now computer-based. Believe me or not, all those types are still in use on the UK railway network. Luckily, we're getting more of the newest ones, but still that's a challenge. And finally, that's where our system comes in, signaling control. So that's roughly the coverage across the country. What's relevant for us is around London, that's Liverpool Street, Marylebone and Paddington. When you're in the control room, you typically see a number of those workstations. So that's kind of 8 screens giving signalers overview what's going on the railway network. And there will be a number of those kind of desks spread around the operations floor. And the key thing is that it allows people to see the current state of the infrastructure. So they can see where the trains are, what's the state of all the signals, and effectively know what's currently happening. And that, again, to ensure safe operation of the train services. So as an example, in this schematic view, which is not kind of geographical but related to, you can see a train occupying that section of the track going this direction, and another one having green signals and moving towards Marylebone. And again, that's from there you can see where things are, but you don't know what's going to happen in half an hour time or in 1 hour, and what's the impact of some of the issues that are developing in this world. In terms of technologies, we use a lot of Eclipse IoT, primarily Eclipse Paho, the Java client, highly resilient and kind of helps with a lot of kind of edge conditions around network availability. So we use it quite heavily. Almost every component of the solution uses the Java client. We use mqtt-spy, which is more of a test tool that we've created specifically for scalable to kind of help with manual and automated testing. And another key component is Eclipse Mosquitto. Again, production grade, lightweight, low latency messaging. And that's really important for us because when something happens on the railway, you want to see the current state of it as soon as possible. So with that solution, we can achieve latency that's counted in milliseconds as opposed to seconds. And that's kind of testament to how good the software is with Mosquitto, we had over 300,000 hours of service without any interruption. So it's really proven technology that works in that safety, critical and safety-related environment. And what's worth noting about scalable as well, the availability we have to reach is 99.9995, which is less than 2.5 minutes of downtime per year. So there are really tough requirements we have to meet, and those technologies allow us to support that. And there is a lot of hardware redundancy and software redundancy in there to make those things happen. There are a couple of things that are worth pointing out, particularly in those kind of environments and some of the considerations we went through. So because we want that low latency in the system, we went for messaging, which is event-based processing. And there it's really helpful to have the pub sub mechanism because the whole solution becomes far more testable in terms of seeing what the system is doing, interacting with it, and so on. And the tendency I see very often in terms of implementing messaging solutions is going for the highest quality of service. You would naturally think that that's what you want to get. But actually when you consider performance, maintenance, you don't want messages to be stored on disk and doing I/O when you've got only milliseconds to move message from one end of the system to another. So again, in that case, the simple in-memory processing works well. And again, in IoT, very often we talk about low bandwidth, kind of low impact, but then we chuck in some JSON and XML, and it just expands the payload so much. So again, that's worth paying attention to. And because the whole kind of change process is very expensive, we've achieved high levels of automation in our solution. That again helps with kind of regression testing. So moving on to Great Western Railway. So that's, as you can see, the line spanning from London, Paddington, all the way through Reading, Swindon and Bristol. And it's quite a complex one in the sense that there's loads of hardware deployed on that network. That's about 65 interlocking, so those IoT gateways that then aggregate all the signaling infrastructure, which is about 3,000 objects. And then there's, again, a few miles of track as well to look after. What are the key challenges on that, or effectively any other part of the network as well, is as a controller, I want to understand the impact of all the interactions between trains. And in one of the previous screenshots, you could see the schematic view and the current state of the railway. From that, it's difficult to see what's going to happen in the very near future, especially when there are delays. So the key challenge there is that when a delay happens, we want to then reduce the knock-on effects of one service affecting other services. Of course, it's difficult to add new resources, new trains, new lines, so we want to make the best possible use of the existing infrastructure. But what's more important is the impact on everyone who's using the railways. So our primary goal is to reduce the impact and reduce delays for people who use it. So that's then the kind of the traffic management solution we'll be putting in place. And what's worth noting here is that we are doing it in a kind of new way with our customer, in a way that the kind of the arrangement that we're going into is then based around sharing the benefits of the reduced delays and improved service. So we're not interested in getting a specification that's 50 pages long and then disappearing for a year or two, taking tens of millions of pounds and delivering a system that's not going to work. We want to make sure it makes a difference on the railway. So when we go through the functionality of the system and develop it, we want to prioritize the functionality that's going to make the biggest impact, and then liaise with our customer and other stakeholders to make sure that that's what we prioritize. So we've seen scalable, which gives us the representation of where things are. Similarly with traffic management, we want to process the data coming from the infrastructure and from the trains themselves. Very often now we'll be going via IoT gateways like the interlockings or kind of on-board train systems. And at that point, we then create a virtual representation of all the infrastructure. So effectively, every interlocking has got a virtual twin, a digital twin in that case, and the same with each train. So we model each train moving around the network, and once we know where those things are, we can run predictions on what's going to happen in the near future. And that's really important because that's the only way to understand the impact of issues that are happening on the network. And then to make a sense of that, we will also want to quantify the problems. So if you've got 15 problems to deal with, you want to concentrate on those that have the greatest impact on all the services running on the network. So our traffic management solution will be able to visualize, evaluate, and effectively automatically resolve some of those issues that are happening, and then allow network rail, train operators, and other parties to review and agree the most appropriate changes that need to be made to reduce the impact on passengers. And once that's been done, we then communicate back to those gateways and other systems. So that's telling signals and tracks and points to go into a certain state. It's advising trains, say, to reduce speed because there is a red signal ahead, so it doesn't go at full speed and then brake. And it's sending that information to passenger information system as well, because when you change a platform at a station, you want to inform the passengers as soon as possible, not 5 minutes before departure, as sometimes happens. So it's about making decisions, making the most optimal decisions, and then implementing them with everyone, so everyone is informed about what's going to happen. So I would like to go through one particular use case and explain how the process is going to work. So imagine there is a delay to a train running from Bristol to London Paddington. And when you then do a forecast of what's going to happen on the network, you can see there will be a number of issues. So first, leaving Bristol Parkway, station through, there are other services going through it as well. Then there might be a headway violation, so that's effectively two trains coming too close to each other, and very often that's the case with slow running trains ahead. When I was coming into London yesterday, that's exactly what happened, following a slow running train. I'm sure you're used to it as well, and then that's it. So again, it's getting visibility of those issues to the controllers so they can take an action that's appropriate. And then finally, say, when you finally hit our final destination, because we're so many minutes late, it's likely there is another train in that platform already. So what do you do in that situation? So that's an early version of one of the tools that we have. You can see a list of locations here that the trains will be going through and a time axis. And that's the common element you're going to see in kind of a traffic management suite is the time and what's going to happen in the near future. And there are a few time horizons we're dealing with. One is the next 2 or 3 minutes where you can't really change much. Everything has been set up, the trains are moving forward. But then there will be issues that happen, like I'm going through a station throw, leaving Bristol, and I need to make sure that that's safe. So the system can automatically optimize that because that needs to happen within the next 10 minutes. And then there is kind of further horizon where the system, based on the forecast, will be able to detect conflicts and kind of raise awareness of those to the user with, again, quantified impact. And what we propose is that first the system will be able to handle those conflicts automatically. And in this case, where we've got a train following a slow running train, depending on the configured parameters, it might be possible to move the slow running train on the relief line and let the fast train achieve its destination as quickly as we can. Or if the delay is too long, then sometimes there are no options to consider. And similarly, our platforms. So that's another tool that we will be delivering, which is a platform Docker. That's a station view, purely focusing on a particular station. In that case, that's Marylebone, which is not the western route, but to explain the process. So we can see all the platforms and the occupancy, we can see the time, and then again any issues. So if we see a train arriving late, it's going to enter the same platform as something that's already there, and then the controller can see, well, there is a platform not fully utilized, can I move it to a different location? And again, we want to make those decisions as soon as possible, because when people wait for the trains, they want to know where to go. And knowing all that information well in advance helps with finding the right resources. And finally, I want to share with you some of the kind of techniques we've implemented or are implementing within our traffic management solution that we'll be deploying early next year. Something we've embraced a lot is behavior-driven development. You might have heard about Gherkin and Cucumber and so on. And where we find it really useful is the business analysts and the developers working together to understand the behavior that is required and then adjusting the implementation to make sure that everyone shares the same understanding of what's required. And then allows us to be more agile as well. So when we identify new features, we can agree what's the scope, what are the changes, and then implement them in a consistent way. Another kind of pattern that we've followed in terms of the architecture this time is backend for front-end. So rather than creating a set of generic APIs that support everything that's possible, we've got APIs and gateways and kind of microservices specific to each of the tools that we have or the platforms they run. So even though all the data that's presented to the controllers is around trains and the network, but very often that's done in a specific way with a specific user in mind. So we're doing that to simplify the UI and how it's kind of being developed. Of course, a lot of continuous integration, continuous deployment. Another thing that we found kind of working better for us in that case, because we haven't got that kind of restriction on low latency and the kind of the millisecond data times from one end to another, is rather than using messaging, as in signal control, we're using REST. And it helps with keeping the solution simpler and then focusing on functionality. And that then allows us to do optimization at a later time. So we're not second guessing where the performance bottlenecks will be, we can then measure it effectively and optimize it in the right place. And another key element with this is the testability of the solution. So as with REST, of course, you try to give for stateless, but that's not always possible. So we're kind of trying to find different ways of testing the solution and then automating it. And something we've tried to employ that you might be familiar with, the test pyramid, where we go through kind of various stages of testing, and as opposed to repeating the same tests, we try to think where we add value with more integrated tests, and then try to reduce the manual testing to the bare minimum. Something that we struggled a little bit with, and I'll be keen to get your views on that, is once you've got your system running with all these microservices, is how you intercept various requests going between those to get visibility of how the system is behaving. And you can do tracing and you can log that, and that's fine, but that's still kind of not as optimal as we would hope. Thank you very much.